Okay. Yeah, so I should tell you what I do, right? And what I think I do is I try to turn data into information. And I think that's an important step. And I have to start off with this, because I do still work at JP Morgan, which is everything I'm going to tell you is my own personal opinion. So this kind of puts the whole talk into a sort of more philosophical vein. But I have been building information out of data for, unfortunately, 22 years now. I started off as a particle astrophysicist doing astronomy with cosmic rays down a mine shaft in Minnesota, which is a bizarre thing to do. We had a data set of about 5 million particle events, which we thought was big data at the time. Through various paths, I ended up working with this guy over here, Peter Muller, who's one of the reasons why I live in the United States. And I think I learned a lot from Peter. And I think the principal reason why Peter is successful is because he said, if you want to analyze data, you have to be a scientist. I now have a job title of data scientist, not quant, not physicist. And I encounter a lot of people who don't really emphasize that word scientist. So let's start off by saying, what is a data scientist? Right, a data scientist is someone who's employed to make inferences from data and is going to do that job in a rigorous scientific fashion. That is not someone who uses these modern fancy tools. This is not someone who knows about scikit-learn. This is not someone who uses big data platforms. This is not someone who's watched YouTube videos about machine learning, right? This is someone who is scientific and careful about what they do with data, and they understand the process of turning data into information. So I like to start off by thinking about, descriptive statistics. This is one way of getting information out of data. This is essentially a dimensional reduction technique. Here we have a scatter of data and we have a linear regression. So we've reduced, I think it's like 25 data points into 4, right? That's a dimensional reduction. When people talk about dimensional reduction, they tend to think about linear algebra techniques, like principal components analysis or independent components analysis or singular value decomposition. That is one way of reducing dimensionality. It's not the only way of reducing dimensionality. Predictive models reduce dimensionality, and that is the purpose of descriptive statistics. They are to get you in the position where you can do predictive analytics. And predictive analytics is something very specific. It means processing historical data to deliver inferential systems that allow you to anticipate the likely values of unobserved data. That's what you're trying to do. Now, sometimes those values are because of a configuration of the world that you can't get access to, right? And climate simulation is one thing. We can't change the configuration of the world. Nuclear explosion simulations. We have stopped blowing up the planet in order to find out what happens when you have a nuclear explosion, but you still do it. Simulations of it. The other thing is you have regions of the data space which you don't have access to, and in finance context, that really means the future, right? So I really think that the key thing about predictive analytics is it's about predicting the future values of metrics that you care about. It's about using the information I have now to look at the conditional distribution of future things, right? And the conditional distribution is an important thing to think about, because we all have different processes that we go through in order to process data, and so we see different future distributions. And the unconditional distribution is the one that you just get from doing your simple descriptive statistics. When you build a predictive model, you see that conditional distribution, which is different. And this is a very, very simple toy example. So we have an autoregressive process, right? It's an elementary thing. The unconditional distribution of the future returns under this model is given by the first formula there, and the conditional distribution, conditioned on the information that I've extracted, is different. And we'll do this graphically. You have two probability distributions. Equally rational people will make completely different decisions based on their views of the future distributions of the metrics that they care about. And in particular, they might make different decisions if they are looking at the conditional distribution versus the unconditional distribution. And it's very important to think that we're not, when we predict the future, what we're doing is trying to tilt that probability distribution, that range of future outcomes, a bit in our favor. That's all you're really trying to do. You're not going to succeed in getting anything right. In fact, more strongly than that, you will be wrong almost certainly. Your job is to just nudge that distribution in your favor. So how do you go about actually doing predictive analytics, right? It's not about building complex models. Sometimes complex models work. That's not the definition of predictive analytics. You're not trying to anticipate, or rather, you're not trying to describe previously observed data, right? In physical sciences, which is my background, you kind of have this view that there's an underlying truth and the measurement process corrupts that truth. And the thing that you're supposed to do is get rid of the measurement process and reveal the underlying truth. And in a financial context and a social science context, I think you really have to embrace the fact that the data you observe is the truth. And I have a simple analogy, right? If you think about the number of people that I talk to today personally, right? It could be drawn from some probability distribution with a expectation of 34, and I observe 48. Right? It wasn't really 34. It was really 48. And I have to process that data differently. I have to accept the data itself is the reality. And that's something that's quite different between processing data in a financial, social science context and processing it in a physical science context. Of course, there is a little wrinkle there, which is you can have both those processes going on, and then you have to start talking about Kalman filters and state-based models and complexities, but we'll just ignore that. Right? When you talk about financial data, I think you really have to embrace in your heart certain truths. And one of the truths about financial data is it is not normally distributed. Absolutely not. And what you have there is a histogram of the daily returns of the S&P 500 index over 10 years, 20 years. The blue histogram is the real data. The red curve is a normal distribution. This data is not normally distributed. It's not close to normally distributed. It's never going to be normally distributed. So you can't do reasoning on that assumption. Here's exactly the same data, just projected onto a time series, right? The idea that the variance is constant throughout time is false. You have to not use that. You have to not do analysis which assumes that. And furthermore, the reason why I have 100 years highlighted on that chart is in 2008, Alan Greenspan was quoted as saying that what was happening was a once in 100 years flood. And I would respond back by saying, does that difference look like 100 years to you? In finance, bad stuff happens all the time. And it clumps together. You have to accept that in the analysis that you do. So if you go build something which assumes that the volatility is constant throughout time, what you're doing is listening to the parts of the curve where the volatility is really high and ignoring the parts of the curve where the volatility is really low. That's the wrong thing to do. So having understood a little bit of the realities of the word, what do you have to do to build a successful predictive model? You have to work where you have an information advantage. People involved in proprietary trading know about that. People involved in big data analytics don't really go through the thought process of thinking, do I have an information advantage? So I spent about 18 years of my life in proprietary trading. You really have to have one or two things in order to succeed. You can have both if you're lucky. Private source of information. That doesn't necessarily mean an illegal source of information, but it does mean a private source of information. You know something someone else doesn't, right? Or you're processing public information much more efficiently than other people are. If you have one of those two things or both, you will succeed. If you don't have them, you will fail. And so you have to work, if you're involved in predictive analytics, work in a field where you have an information advantage. That works for hedge funds, that applies to proprietary traders. It also applies to big old banks, which is where I work right now. So I should make sure I have an information advantage and work where I have one. There are places within the bank where I have an information advantage. One of the businesses that we work with is the credit business, bond trading, right? It's a very illiquid market. JP Morgan has a 60% market share in that market. So they have information that other people don't have. There are private data sets that we have. Another thing that we work with is the investment banking business. they have sales notes that are their own private information. You can work with that information to give them predictions about which companies they should call, create lead generation tools, who to call lists, what to pitch lists. What I should not do, and I am hiring a lot of people, and I talk to a lot of people who are sort of influenced by this current environment we have, West Coast data science, and they tell me that they are downloading data from Yahoo Finance and going to use machine learning algorithms like support vector regression, and they're going to make a lot of money doing that. And my response to them is, you are going to give a lot of money to KCG, and then you're going to stop, right? Because everybody has that data, everyone has those methodologies. You are competing in an area where you don't have an information advantage. So you need to work where you have an information advantage. And if everyone can get access to your data, it's not going to work for you. So it's not just enough to have that information advantage. I need to measure it, right? You can build a linear regression model to look at how today's returns relate to yesterday's returns. You can build a support vector regression model to do the same thing. Just because you can build a predictive model doesn't mean it's a good thing, right? I can predict the temperature in Midtown Manhattan tomorrow. It's currently 71 degrees, so I predict it's 71 degrees. Is that better than the National Weather Service, right? Just because you can make a prediction doesn't mean it's something you should be doing, which means you need to measure the values of your predictions. And the only way to measure them is measure them relative to a benchmark. So when I'm talking about measuring relative to benchmark, then I have to get into these metrics. Which one you like depends on your context. You can do relative forecasting skill. They actually use that in the weather industry. Information ratios you use in finance. If you want to get a bit more technical about probability distributions, you can talk about Kullback-Leibler divergences, right? If you want to go back to simple statistical analysis, R squared, how much variance do I explain, right? And compare it to the benchmark, and that's important. The other thing that's really important is causality, right? Many of us, I'm sure, have seen regressions that are things that don't work. It's not enough that data needs to be related. It's important that the causal relationships between what I can observe and what the consequences of my observations are understood. And one thing that I think is important is the analysis of causality, in many cases, relies on judgment. You look at the data and you go, oh, that doesn't make sense. And I don't think that's the right way to do it. I think it should be algorithmic. I think there are procedures which have been developed. They're not perfect, but they do allow you to address questions of causality. So these are a couple of fun examples. You can go to the internet. You can find many, many examples of spurious correlation. So on the left-hand side, we have the number of storks nesting in Brandenburg in any given year. And on the vertical axis, you have the number of babies born at home in Berlin. Right? The R squared is 43%. Is this a causal relationship? Do storks bring babies? And we say no, right? We know this is ridiculous. On the right-hand side, you have crude oil imports into the United States in billions of barrels, right? And on the vertical axis, you have chickens consumed per capita, right? Is that a causal relationship? Well, if I'm analyzing that as a human being, I start to create an argument, right? Chicken is a substitution good for beef. The amount of crude oil imports versus domestically produced might be a function of the operations of the US economy, and therefore that's going to affect the take-home pay of workers, and that's going to affect whether they substitute from beef to chicken, okay? Both of these relationships fail a Granger causality test, right? It's a very simplistic test. It's not necessarily the best test, but if your data fails a test like this, I'm going to say you probably don't have a causal relationship. Right? So you need to be very careful when you do this kind of analysis. One thing that I think we need to be aware of is geometry of financial data. The shape of the data space you're working in is different to that in the retail data space. If I'm building a system, so I'm at JP Morgan, the investment bank, not Chase, the retail bank. We could build a machine learning system to help a retail loan officer. That's quite different to building a machine learning system to help a bond salesman. In the first context, you're trying to get the work of one loan officer replicated easily and cheaply, right? One officer might do a few hundred loans. An algorithm can do tens of thousands of loans. And what you get from the machine is scale, predictability, reproducibility, low operating costs, and 24/7 coverage. If I am working in a context where a large number of people are trying to evaluate a small number of data points, which is a market, I get different behavior, right? One of my favorite examples I like to talk about, other people have heard me mention this before, is a paper from Richard Roll in 1984 in which he showed that weather does not predict futures prices, but future prices predict the weather, right? So the causality is not what you expect, right? But if you know about financial markets, you would expect that, right? I have maybe 300 or 400 people at the time he was doing this standing in a room in downtown Manhattan trying to figure out what's going to happen to frozen concentrated orange juice prices, right? They are lots of people trying to predict one thing, the price of orange juice tomorrow. And that's a different environment from one machine, one person trying to predict 1,000 things. In the same thing you get from the machines, you get scale, predictability, reproducibility, low operating costs, 24/7 coverage. Yes, they do exactly the same. It's not necessarily more accurate than a crowd of people, which refers back to the talk this morning about the wisdom of crowds. Just because you can use a computer to do it doesn't mean it's the best way to solve the problem. And you will find that it is very cheap to go to things like Amazon Mechanical Turk or Crowdflower or these kinds of companies where you get crowds of people having opinions, and you get better answers from those environments than me sitting down and producing some kind of fancy machine learning model, right? So you want to work where you're doing something useful with your technology. Here's the weather data. This is kind of fun. So the x-axis is the return of the orange juice futures contract from the first delivery date to the last trading date. And the y-axis is the error in the National Weather Service prediction for the temperature in Orlando from the last trading date to the last delivery date, right? So that's this period of time, I see what's happening to the prices. This period of time, I correct the weather forecast. That's fairly impressive, right? And this is something I think really needs to be in our minds. If we're building machine learning systems, if we're building analytical systems, can we do better than a crowd? And if we can't, don't try. Going back to what makes financial data, I believe, actually quite different to retail data. In finance, everything is correlated, right? Your base assumption should be that. You could describe it as a martingale or a random walk or a unit root process, whatever you want to do. Data is serially correlated with itself, and that has a very profound effect on how you analyze it, right? In the talk earlier this morning, there was discussion of not doing optimization in a time series context because it's hard. Well, finance operates in a time series context, and it is different to process data that way. And again, going back to simple benchmarks, a very good predictor of the price of IBM tomorrow is the price of IBM today, right? If you're going to build a machine learning model to predict prices, you've got to beat that, right? I'm not saying that you can't, I'm saying that's what you have to beat. The other thing where correlation exists, which a lot of people in quantitative finance know, is cross-sectionally. You pick two stocks at random, their return's going to be 30, 40% correlated, right? We have this notorious little beast here, which is a copula. And the reason why I've written that down specifically is here's a theorem that tells you how to relate a multivariate distribution to the marginal distributions. And the linkage function, the copula, that is not unity. That is not close to unity. These multivariable, these data series are involved with each other a huge amount, and you cannot be successful if you ignore that. So here's an example of data that's correlated, right? So you have the monthly log returns of the VIX index on one axis and monthly log returns of the S&P 500 on the vertical axis, right? And this correlation, I believe, is about minus 80, minus 90%. You know, that's huge. So you often see this if you watch CNBC, something I used to do and have kind of kicked the habit. They say, in the same breath, the market fell today and the VIX rose. Well, you know what? Those are the same pieces of information. Saying it twice with different labels doesn't make it different. So everything is correlated. The other thing which is really true in financial data is you get power law distributions. You get power law distributions all over the place, right? So here are a few examples. If you go to the New York Stock Exchange, you go to BATS, whatever, a few stocks represent a significant fraction of the total volume. If you go inside JP Morgan, a few clients represent a significant fraction of all of the volume that we do. And in this case, we're talking about people like BlackRock and Fidelity and those firms, right? So if you're processing data in a retail context, and I aggregate together all of the buying patterns of the millions of people who buy things from Amazon, I am removing idiosyncratic details and exposing underlying factors. If I were to go to all of the bond sales done by the JP Morgan credit desk and do the same aggregation, what I get is a bad measurement of BlackRock's trading behavior, right? Because they are so dominant because of these power law structures that the averaging doesn't get rid of it, right? And you need to be aware of that. And the final quote I like, this is from Peter Thiel in his book 0 to 1. A few private equity investments deliver substantially all the portfolio returns. And furthermore, it's pretty hard to predict which ones they're going to be. And his argument is just basically bet on everything. Right. So here's our power law. I took this from the Bloomberg. S&P 500 members, total dollar volume share, measured at 2 p.m. on the 25th of April, right? The dots are the volumes. What you have is a chart where you have the share of total volume on the y-axis, and the x-axis is your rank within that distribution. You can see the data is very well organized. The red curve there is what's called the Zipf-Mandelbrot law, right? Hermann Zipf was a Harvard linguist. He looked at the distributions of words in languages, and he discovered a power law in the relative frequency of words in languages. Mandelbrot, who did a lot of really cool work on pricing commodities in the 1950s and 1960s, he modified that distribution slightly. What he did is he made it turn over a little bit at the end. But you can sit down with financial data, you will find power laws, right? Power laws have different convergence properties to polynomial functions, right? They are going to mess things up when you do data analysis, and you need to be aware of that. This is a lot of people spend a lot of time talking about cleaning data and removing outliers, and I think it's very important to, when you're going about analyzing data, to understand the difference between an outlier and a contaminant. The following things happened during my career in finance so far, right? I've blended it a little. I went up to Oxford in October 87. So the crash happened pretty much like the first week after I got to college. But 1994, interest rate shock. I was a graduate student, but I was actually trading equities and UK government bonds on my own account. At that time, I thought I was a genius until Alan Greenspan changed the interest rate policy of the United States, and I lost a lot of money, right? Kobe earthquake. I was on the Japanese warrants trading desk in London at Morgan Stanley when the Kobe earthquake happened. I saw people change from having a miserable year to an unbelievable year in the space of a few hours, right? The Asian currency crisis, the Russian default, long-term capital management. I was trading Eurodollar futures at Morgan Stanley during long-term capital management. The dot-com bubble. I was on the Morgan Stanley trading floor when Netscape was priced. It was the most surreal moment I've ever experienced, I think, still. The dot-com crash. 2007, all the quant fronts bombed at the same time. 2008, we got the financial crisis everyone knows about, various flash crashes, zero interest rate policy. How many databases were built on the assumption that interest rates can't be negative or zero, right? There are various stochastic process models for interest rates where they have that the volatility of interest rates is proportional with some power spectral index to the level of interest rates. That volatility goes to zero in that model, and it disappears completely when the interest rates become negative, as they currently are in many countries in Europe, right? So these bad things are real things, and when you analyze data, you need to be aware of them. So I am not saying don't clean data. I'm saying be aware of what you're doing and understand the effect of the actions that you take on the inference system that you're building. How I pre-process data matters, right? My decision-making system, which is the output of my alpha generator or my predictive model, is in reality going to experience all of those bad things if they're real things. How is it going to behave? If I do things like mean imputation, right, then I'm going to underestimate my process variance because I'm saying a lot of the data points are exactly the same when they weren't. That leads me to overestimate the significance of the parameters I use in whatever model I build, whether it's a fully parametric traditional statistical model or some machine learning model, doesn't really matter, right? That means I'm going to build models that fail out of sample, right? So that simple task of just saying I'm going to do mean imputation means that I am more likely to build models that don't work. One thing that when I started this, a lot of people were doing with futures data is fill forward, right? What does fill forward do to the data? It induces momentum, right? So be aware that these simple things, you sit down in front of the computer, you're like, oh, I have an NA here, I need to fill it with something so that my R code will actually output something, right? What I do then, and I spend 1 second thinking about it, affects the model that I actually get, and it biases it towards something which is not going to work as well, right? Additive noise, that produces mean reversion, right? So you have to just be really careful and understand the impact of all of these stages when you process the data, okay? I showed this chart of the S&P 500, and I said it's not normally distributed. Okay, so you can prove this. Everyone knows this. Least squares is the best thing to do when you have homoscedastic normal distributions. Financial data is not homoscedastically normally distributed, right? Least squares is not the most efficient method to analyze your data. Okay, we're not in linear regression world. How many machine learning algorithms minimize the mean squared error? Most of them, right? So they are implicitly assuming that the residuals between the model and the observations are normally distributed. They're not, right? What does our experiences tell us about the assumptions of making these kinds of assumptions? Well, we can go back to the previous list, right? Finally, and I think this is really true, and you need to think about, we are in an environment where we throw around this word big data. And many people are like, what does big data actually mean? And this is my thought process regarding this, and it impacts how you build a model, right? I'm going to start with unconstrained optimization, right? Let's find a solution which satisfies your objectives, right? And then there's something else you can do, constrained optimization. If you look at constrained optimization routines, starting with the simplex algorithm, right, you find a feasible set. You find solutions which are defined by your constraints, and then you sort between them. Those two actions are radically different, right? Do you want to solve something according to your objectives, or do you want to solve something according to your constraints? What's happened in big data world is we've had radical transformations in the costs and capacities of storage and compute. And so when you're thinking about doing a data analysis on a data set, think about this. How would you behave differently if storage wasn't cheap? How would you behave if storage was completely free, right? If I removed the constraint. How would you behave if compute was completely free? It's cheap, but what if it was completely free? That changes your constraints, it changes your behavior. So, if storage is free, store everything in the format it arrives in, rather than normalizing it to a scheme that I currently think is the right thing. Enhance your primary data, decorate it with added value features, rather than changing it, rather than replacing it. Stop deleting data you don't need to delete to save space, because you don't need to save space because storage is free. Stop deleting data that you don't think you currently need because you think it'll be too expensive to plow through all of it, because compute is expensive, because it's not. Compute is free. This is a sort of very technical thing, but there's this thing called normalization on read. What that means is I have my data and I make it look like I want it to look at the time I'm processing it, as distinct from normalization on write, which means I define how it's going to look and I damage it to fit that format at the time I store it. If I do the latter, I'm destroying data by design. Don't do that. This works if you have a data model that's scalable, right? Data is one of the few commodities you're going to come across that has increasing returns to scale. Big firms like JP Morgan, other big banks, other big institutions, they have many, many silos. The value of the data is, when it's siloized, just a function of the number of silos you have. If you can create a data model which links together those silos, the value of the data is more than the number of silos, and it increases with the number of resources you bring online. And sharing that data model allows everyone to benefit from that and brings you more value coming in. And sharing the data model is important. And if you think about the operations of internal trading desks, in finance, everyone's like, I have a big secret, no one can know what I know, despite the fact that 2007, every single quant fund crashed at exactly the same time, so they all apparently had the same big secret that no one else was allowed to know, right? So share your data model within your lines of business. Share your data model with your clients. If you're a systematically important institution like JP Morgan, you have to share your data model with your regulators. And I feel maybe even share your data model with your competitors, right? If we can talk together, we can trade together better. And going back to the economic theory, right, when you have comparative advantage, you trade and everybody gets better, right? So sharing that data model makes everyone better. And I think these are things that we can now do with the technology that's available. We did things in the past. When I was at PDT, everything was based on linear regression. That wasn't because we thought linear regression was right. It was because it was the only thing we could do with the computers available at the time. Now we have computers that can do much more complicated things. And we shouldn't let the constraint of computation stop us doing what we want to do. Any questions?
One here. I'm just wondering, when you do predictive analysis, what kind of assumptions are you making on rationality? Are you assuming everyone is rational, or are you making adjustments for behavioral biases?
I think it really depends on the context, right? And depends what you're trying to do. I'll be concrete about it, right? One of the examples where we're assuming there are biases are we're doing a system in which we're trying to identify which clients have adverse selection against the block trading desk, right? So there's private information there, right? Which is the clients know what they're doing and we don't. Another situation in which I'm actually assuming people are rational is we're building a system, well, not building, we're leveraging an existing system and trying to enhance it, where we propose bonds for credit clients. And what we do is we rank them by the client's propensity to buy, as distinct from ranking them by expected future returns. And that's really on the assumption that they know what they're doing, right? And that we really don't know what they're doing. So the fact that we have a particular bond in inventory isn't the reason why we should try jam it down their throats, right? We should use their observed historic trading patterns and infer what their preferences are and assume that they actually know what they're doing. And I'm a big fan of assuming as a first order cut that people actually do know what they're doing when they're financially motivated.
In your view, what are the best practices to avoid overfitting and better out-of-sample performance?
Okay, I think the absolute best thing to do to avoid overfitting is to connect yourself to a hosepipe of fresh data coming in. You see in a machine learning context, in a data science context, a lot of people, and they talk about cross-validation and five-fold cross-validation, and my answer is, who told you 5 is the right number, right? And no one ever addresses that question, right? If your decision is a function of your entire data set, it's in sample. If you decide to mess it around in some way, good for you. Maybe that makes your procedure more efficient. It's still in sample. If you hold out data, which you're kind of compelled to do a lot of the time, that's not a real experience, because guess what? You're not going to eat the P&L of historic data even if you haven't trained your systems on it. If you want to really find out if what you're doing makes sense, connect it to live data and see what happens. And you will find the errors and the biased assumptions you've made so fast when you're watching that P&L chart tick up and down compared to, oh, you know, my R squared is 12% and like it has 7 factors and it's parsimonious and it passed like XYZ test and I back tested it and I out of sampled it and like it's not the same. Trust me. You know?
I think we have time for one last question over here.
I have a two-part question. The first part is, I mean, if you're a JP Morgan and virtually the universe is your client, then it makes a certain amount of sense to share and be transparent with respect to behaviors, including data.
I absolutely agree with that.
Okay, if you're a small firm and your only advantage might be something that you have eked out either out of the data or from that standpoint, in this incredible presentation, the one thing I didn't see was if you had a different utility function than the universe. And if that's when, in fact, was what you were operating on, and there, and only there, might you be able to get away with not having absolutely the best search methods and techniques to be able to deal with it, but just a way how to extract, so to speak, your own alpha. Do you agree with that part of it as well, from the standpoint of if you have a different utility function, you might be able to get away with not having all those incredible extremes that you had in that list?
I absolutely think your decisions are a function of your utility and your information. I think it's easier to pin down what your information is than what your utility is. But I agree with you, yes.
Thank you.
Graham, thank you. That was excellent.
Thanks.